We will wait for a couple of more minutes, about 7:05, and then we can start today's session. Hello everyone, good evening. I am Rahul Patel from Department of Chemical Engineering, IIT Bombay, and I am conducting these hourly weekly sessions to solve the previous year GATE questions, and right now we are looking at heat transfer subject. I hope I am audible and the slides are visible too. If you have any problem, you can just write it in chat box. Okay. So the first question that we are looking on is from GATE 2017 paper. I will just quickly read the question and then we can look at the video solution. The question is, in a heat exchanger, the inner diameter of the tube is 25 mm and its outer diameter is 30 mm. The overall heat transfer coefficient based on the inner area is 360 watt per meter square degree Celsius. Then the overall heat transfer coefficient based on the outer area rounded to the nearest integer is dash watt per meter square degree Celsius. So in this question we have been given a double pipe kind of heat exchanger and we have been given this heat transfer coefficient based on the inner area, and we have to find the overall heat transfer coefficient based on the outer area. So ultimately we will be applying the energy balance, that is the heat transfer rate will be equal to UA delta T, and we will be equating for both the cases to find the overall heat transfer coefficient based on outer area. So I'll just play the video solution. Hello everyone, we are solving question 13 of GATE 2017 Chemical Engineering paper from the subject of heat transfer. The question is, in a heat exchanger, the inner diameter of the tube is 25 mm and its outer diameter is 30 mm. The overall heat transfer coefficient based on the inner area is 360 watt per meter square degree Celsius. Then the overall heat transfer coefficient based on outer area rounded to nearest integer is dash. So in this question we have been given a heat exchanger and the corresponding dimensions of the tube as well as the outer tube, and we have been given this overall heat transfer coefficient based on the inner area, and we have been asked to find the overall heat transfer coefficient based on the outer area. So let's just draw a schematic of that heat exchanger. So this is our inner tube for which the diameter we have been given as 25 mm. This is my outer tube for which the diameter D0 is given as 30 mm, and UI, that is heat transfer coefficient based on the inner area, we have been given as 360 watt per meter square. Now if we write the overall heat balance across the heat exchanger, so that we can write it as overall heat balance. So it is given as UI AI into delta T, where delta T will be, so let's just consider if the outer temperature, if the ambient air temperature is T1, at the surface it is T2, at the surface it is T3, and here it is T4. Then the total Q, that is heat exchange, will be due to this temperature difference across T1 and T4. So that we can write it as UA T1 minus T4. Okay, so here delta T is T1 minus T4. Similarly for the outer case also it will be same. So delta T will be same for both the cases, that is T1 minus T4. Now this delta T we can cancel it out. UI we have been given as 360. AI we can write it as 2 pi inner radius Ri into L is equal to U naught we have to find into 2 pi R naught into L. 2 pi L will get cancelled out and we will get U naught is equal to 360 into Ri upon R naught. We will replace the value of Ri and R naught, which are given as 25 and 30. Okay, so 360 into Ri upon R naught. Yes, Ri we have been given as 25, and R naught we have been given as 30. So this will come 12. So the answer will be 300, and the units are watt per meter square degree Celsius. So yes, we can report the final answer as 300 watt per meter square degree Celsius. Okay, so this was a fairly simple question. If you have any doubt, you can ask, and we can move on to next question in a couple of minutes. This is question. Now let's look at the next question, that is question 39 from GATE 2017 chemical engineering paper. This is a fairly straightforward question in which we have been asked that let IB lambda with the spectral blackbody radiation intensity per unit wavelength about the wavelength lambda, the blackbody radiation intensity emitted by the blackbody over all wavelengths is. So let's just solve this question over here only. So we have been given IB of lambda, that is blackbody radiation intensity, intensity per unit wavelength, that is lambda, and this is about the wavelength lambda. So for the wavelength of lambda, we have been given the spectral blackbody radiation that is given by IB lambda, and we have been asked to find this across all the wavelengths. So we will be basically integrating this IB lambda terms from 0 to infinity across all the lambdas, and this term is known as my blackbody radiation intensity. So basically we were given IB lambda for a particular wavelength. To find this blackbody radiation intensity over all wavelength, we have to just integrate it over lambda. That will give us the blackbody radiation intensity. And this blackbody radiation intensity is used to define this term blackbody radiation as EB given IB. So here we have been given that IB is the total intensity of radiation, and it is defined as integration of 0 to infinity IB lambda and d lambda. So yes, from the given option we can select option C as the correct option. Now let's look at question 40. If you have any doubt, you can write it in chat box or unmute yourself and speak up too. So I guess we can move on to next question. The next question is question 40 of GATE 2017 chemical engineering paper, and the question is: a fluid flows over a heated horizontal plate maintained at a temperature Tw. The bulk temperature of the fluid is T infinity. The temperature profile in the thermal boundary layer is given by this equation. Here y is the vertical distance from the plate, delta T is the thickness of the thermal boundary layer, and K is the thermal conductivity of the fluid. The local heat transfer coefficient is given by which of the following option? So we have been given the temperature profile, and we have been asked to find the local heat transfer coefficient, that is Hx. So basically we know that Q will be Hx into delta t, and this will be equal to k del t by del y at y equal to 0. So we will be using this equation to find our hx. This is the basic concept that will be used in the question. Now let's look at the video solution to know the detailed solution of this question. Hello everyone. We are looking at question 40 of GATE 2017 chemical engineering paper from the subject of heat transfer. The question is, a fluid flows over a heated horizontal plate maintained at temperature Tw. The bulk temperature of the fluid is T infinity. The temperature profile in the thermal boundary layer is given by this equation, where y is the vertical distance from the plate, delta T is the thickness of the thermal boundary layer, and K is the thermal conductivity of the fluid. The local heat transfer coefficient is given by, so we have been given 4 options and we have been asked to select the correct option corresponding to the local heat transfer coefficient. So as given in the question, we will draw the schematic. A fluid flows over the heated horizontal plate maintained at temperature Tw. So let's just consider this is our heated plate and the temperature we have been given as Tw. The bulk temperature of the fluid is T infinity, and we have a fluid flowing through this plate. So correspondingly the profile will be like this, and where we have been given delta T is the thickness of the thermal boundary layer. So if this is my thermal boundary layer, Harshal, can you hear me?
Yes, sir, but video's sound is not coming.
So is the volume low or very?
I try with high volume, sir, but there is no sound is coming of video.
Okay, let me play it again. Then we have been given as this is delta T, that temperature fluid. The local heat transfer coefficient is given by, so we have been given 4 options and we have been asked to select the correct option corresponding to the local heat transfer coefficient. So as given in the question, we will draw the schematic. A fluid flows over the heated horizontal plate maintained at temperature Tw. So let's just consider this is our heated plate and the temperature we have been given as Tw. The bulk temperature of the fluid is T infinity, and we have a fluid flowing through this plate. So correspondingly the profile, Prasanna, Naveen, can you unmute? Can you mute yourself, or should I? It will be like this. The bulk temperature of the fluid is T infinity, and we have a fluid flowing through this plate. So correspondingly the profile will be like this, and where we have been given delta T is the thickness of the thermal boundary layer. So if this is my okay, so I will just solve this question and then we can figure the question. Okay, so let's just solve this question online only. So here we have been given temperature profile and we have been asked to find the local heat transfer coefficient. So ultimately this local heat transfer coefficient, we define it as Q of x is equal to Hx. Then if we have this temperature profile as Tw and this is T infinity, this is how my velocity profile will look like. And then we will be having the thermal boundary layer of thickness delta T over here. Then the direction of heat flow will be from here, that is this wall is maintained at a fixed temperature and fluid is flowing over this wall. So this direction of heat flow will go here and the temperature difference will be Tw minus T infinity. And then we have this K del T by del Y at y equal to 0. Okay, so we will differentiate this temperature equation with respect to y and equate it to 0 to find this del T by del Y at y equal to 0 and put it in this equation to get the ultimate value of Hx. So that is Hx Tw minus T infinity into K del by del Y of this entire term over here. So this will be 0 plus Tw minus T infinity into 1 by 2 then 3y square upon, it will become delta T cube, minus of 3 by 2 derivative of y will be 1 upon delta T, and here we have to put y equal to 0. Okay, so basically this both term will get cancelled out and we will be having Hx equal to K, then what do we have, 3 by 2. So now we will be putting y equal to 0, so this entire term will get cancelled out and we will be having minus of 3 upon 2 delta T. And yes, in this equation we have this minus over here, so basically Qx will be minus of K times of del T by del Y. So ultimately we will be having, this will be equal to 3K upon 2 delta T. So this is my equal to Hx, that is my local heat transfer coefficient. Yes, so from the given option we can see that this option matches our calculation, so we can select option C as the correct option. So from the given option we will select this option C as the correct answer. So if you have any doubts you can just ask. So I will just stop sharing my screen for a bit and just figure out why wasn't the audio coming in the video. Just give me a couple of minutes. So I don't think today we can play the video solution, so we will just solve the questions online for this class. Okay, so let's look at this next question. This is question 41, in which we have been given in a nucleate boiling, the pressure inside a bubble is higher than the pressure surrounding the liquid. Assuming that both liquid and vapor are saturated, the temperature of the liquid will always be dash. So let's just look at the solution over here. So here, first of all, we have been given nucleate boiling. So in nucleate boiling, let's consider this as a vessel, and this is my heat source Q dot, and the vessel is filled with fluid. Then in nucleate boiling regime, the bubbles will start to form. So if we look at one such individual bubble over here, and this will be filled with vapor, and on the outer side it will be liquid. So in this question we have been given the pressure inside the bubble is higher than the pressure of the surrounding liquid, that is Pb is greater than Pl liquid. This we have been given. Now we have been given both the liquid and vapor are saturated, that is liquid and vapor are saturated. Now we have been asked that the temperature of liquid will always be and we have been asked to compare the temperature of liquid with temperature of vapor. So if the temperature of liquid is L, then what is the relation between temperature of liquid and temperature of vapor? So yes, so we know that there is this Antoine equation that is used to correlate the pressure and temperature at the saturation. Okay, so we can write the Antoine equation as ln of P set is equal to A minus B upon T plus C. Now here T and P are corresponding to the saturation temperature and pressure, and this B term, we know that this B term will always be positive. Okay, so now from this equation we have to find that how pressure will change with respect to this saturation temperature. So let's say if my temperature increases, with increasing temperature this entire term will decrease, and okay, with this entire term will decrease. Okay, and ultimately this term will increase. Okay, so from here we have this P set is proportional to, wait a minute, if this increases this term decreases, and this term will increase. So P set is proportional to T set. Wait a minute. So from this equation here I have written that P is inversely proportional to temperature. So from the Antoine's equation we can use this equation, that is the pressure is inversely proportional to temperature, and in the question we were given that the pressure inside the bubble is greater than the pressure inside the liquid. This we were given, and ultimately we can use this correlation over here and find that the temperature of liquid will be less than the temperature of vapor. So we will be using this Antoine equation to find this relationship between pressure and temperature at saturation pressure, and then ultimately use to correlate it with this temperature of liquid and vapor. So right now I'm not playing the video solution, we are just solving the questions online. That is why you are able to hear me. Okay, so in this given question, the temperature of liquid will always be less than the temperature of vapor from we obtained it from over here. Okay, so if you have any doubt in this previous question, you can ask, or else we can move on to the next question. That is question number 9 of GATE 2016 paper. So I guess we can move on to the next question. So this next question is from GATE 2016 paper, and the question is: a composite wall is made of 4 different materials of construction in the fashion shown below. The resistance of each of the section of the wall is indicated in the diagram. So, and we have been given diagram the overall resistance of the composite wall in direction of heat flow. So basically we have been given a slab, and these are the corresponding resistance. So if we mark this as slab 1, this is slab 2, slab 3, and if this is slab 4, then we have been given this direction of heat flow, let's say Q, and then there will be this first resistance, and then we have these two resistance in parallel. Second and third resistance are in parallel, and then we have this fourth resistance in series. So R1, R2, R3 and R4, we have been given the values of this resistance, and we have been asked to find the overall resistance. So we can just simply use the resistance, the formula for resistance in series and parallel to find the overall resistance. So let's solve this for 2 and 3. The overall resistance will be 1 upon R23 is equal to 1 upon R2 plus 1 upon R3, and this will be equal to 0.25 plus 1 upon 1. So this will be 4 plus 1 is equal to 5. That will give us R23 is equal to 1 by 5, that is 0.2. Now the overall resistance will be R total is equal to R1 plus R2 plus R3, and that will be equal to 3 plus 0.2 plus 0.7, and the final answer will be 3.9. Okay, so the final answer will report it as 3.9, and we have been asked to round off till first decimal places, so the final answer is already up till one decimal places, that is 3.9. So yes, we will report the final answer as 3.9. I hope that question was also easy to solve, and now we can move on to question number 10 if you don't have any doubts. So the next question is from boiling and condensation topic of heat transfer, and the question is: steam at 100 degrees Celsius is condensing on a vertical steel plate. The condensate flow is laminar. The average Nusselt's number are Nu1 and Nu2 when the plate temperatures are 10 degrees Celsius and 55 degrees Celsius respectively. Assume the physical properties of fluid and steel to remain constant within the temperature range of interest. using the Nusselt's equation for film type condensation, what is the ratio of Nu2 upon Nu1? So let's say here we have been given a vertical steel plate, and the plate temperatures are 10 degrees Celsius for first case, and for second case we have been given it as 50 degrees Celsius, and steam is condensing over this plate, so it will condense like this, and we are having this film type of condensation. Now for film type condensation, you need to remember this correlation, that is Nusselt's number is inversely proportional to delta T raised to 1 by 4. So this thing you can remember. This correlation basically comes from the Nusselt's number correlation for the film type condensation, which we can write it as this Nusselt's number is equal to 1.13 into rho L upon rho L minus rho V into G HFG L cube upon mu L KL into delta T upon raised to 1 by 4. So this is the overall Nusselt's number correlation for film type condensation. And in this question we have been given that the physical properties of the fluid and steel remain constant within the temperature range of interest. So ultimately all these parameters will remain constant. So that is, we write this as Nusselt's number is equal to K upon delta T raised to 1 by 4, where K is my proportionality constant. So now for both the cases we can write that Nu2 upon Nu1 is equal to delta 1 upon delta T1 upon delta T2 raised to 1 by 4, and delta T1 so this steam is at 100 degrees Celsius, so delta T1 will be 100 minus of T1 is 10 upon 100 minus of 55, oh this was 55 raised to 1 by 4, so ultimately it will become 90 upon 45 raised to 1 by 4, that is 2 raised to 1 by 4. You can calculate this 2 raised to 1 by 4 in Cal C, and it will come around somewhere around 1.189. So yes, from the given option we can select option C. So I don't think you need to remember this entire formula to solve this question. You can just remember two main things from this formula, that is for film type condensation, Nusselt's number is proportional to this L cube and this delta T raised to 1 by 4. So usually questions will come across these two questions only, if the delta T changes or if the length of this vertical steel plate changes. So all you need to remember is this thing, K upon L raised to 3 by 4 upon delta T raised to 1 by 4. So if you remember this correlation, that much is sufficient to solve most of these questions related to film type condensation. Okay, so in this solution also we use the same approach, and the final answer is 1.19. Okay, so if you don't have any doubts, we can move on to next question. Okay, so let's read the next question in detail. So in the experimental setup, mineral oil is filled in between the narrow gap of two horizontal smooth plates. The setup has arrangements to maintain the plates at desired uniform temperatures. At these temperatures, only the radiative heat flux is negligible. The thermal conductivity of oil does not depend perceptibly in this temperature range. Consider 4 experiments at steady state under different experimental conditions as shown in figure below. The figure shows plate temperatures and the heat flux in vertical direction. Okay, so the plate temperatures and heat flux are in vertical direction. And what is the steady state heat flux in watt per meter square with the top plate at 70 degrees Celsius and the bottom plate at 40 degrees Celsius? So for this experiment 4, we have been asked to find the heat flux. Okay, so let's look at each of these cases. So in the first case, the delta T is 30 degrees Celsius. Here also it is the magnitude of temperature difference is 30 degrees Celsius. In all the cases, we have been given 30 degrees Celsius as delta T. Now, if we consider this experiment 1, here we were given that only radiation is negligible. That means either convection or conduction would be taking place, or both can also take place. Now, in this specific case, since the bottom plate is at a higher temperature as compared to the top plate, that means convection would occur in this case. Basically, due to buoyancy, there will be flow within this mineral oil, and that would be accountable for the convection. So in this first case, we will be having convection plus there will be conduction within the fluid as well as the plate. So in the first case, we have convection plus conduction. Now in the second case, since the bottom plate is at lower temperature and the top plate is at a higher temperature, convection won't occur because the heated fluid will remain on the top side and the flow wouldn't happen within this due to this density difference or buoyancy. So here we only have conduction. Similarly, for this case also, we will be having conduction plus convection, since the bottom plate is at a higher temperature as compared to the top plate. And in the last case, we will be only having conduction. So see, the fluid is remaining same in each of this plate, in each of this experiment, as well as the plate is also remaining same. So basically the conduction, the heat transfer due to conduction will remain same, whereas the heat transfer due to convection will change based on the temperature of the bottom plate. That is why in experiment 1 and experiment 3, even though the delta T is same at 30 degrees Celsius, the heat flux is different. Now if we look at experiment 2 and experiment 4, here we are only considering, we will be only having conduction, and since delta T is also same in both the cases, the heat flux will be equal to 26. Heat flux will be same as experiment 2, that is the heat flux will be equal to 26 watt per meter square. So yes, from the given options we can select option A, that is the heat flux will be 26 watt per meter square. Now it won't be equal to 39, 42 or 63 because since they are very high as compared to this term. So yes, this is the basic concept used in this question related to this experimental setup of this, related to this experimental setup. If you have any doubts, you can speak up or just ask, and then we can move on to the next question. So let's move on to the next question then. So for the next question, we have been given the space between two hollow concentric spheres of radii 0.1 meter and 0.2 meter is under vacuum. So here we have been given two spheres. Let's just consider this as sphere 1 and the outer sphere as sphere 2. So ultimately this will look like this. So we have just shown a cross section of that sphere over here. Exchange of radiation occurs only between outer surface S1. Okay, so that means the radiation will only occur in this direction for the first sphere, and the inner surface S2 of the larger sphere. So for the larger sphere, the radiation will only occur in this direction. It won't occur from the outer direction. Now we have been asked that the fraction of radiation energy leaving S2 which reaches S1. So that is basically we have been asked to find F21 is equal to question mark, and F21 we defined as this radiation energy leaving S2 and leaving S1. So now there are these two basically additivity rule for this view factor correlations. That is, the additivity rule will say summation of Fij will be equal to 1. That is, for this question we can write F11 plus F12 is equal to 1. Then there is this reciprocity theorem which gives us A1 F12 is equal to A2 F21. This is known as reciprocity theorem. And this is known as additivity theorem. So yes, these are how these view factors are defined that I already mentioned it too. That is, F12 is defined as fraction of energy leaving surface 1 which reaches surface 2, and F2 is defined by vice versa. Then this is how we derive this reciprocity theorem. So from this here we will be getting A1 F12 is equal to A2 F21, and then over here bottom we have this additivity rule. So we will be using this to solve our question. Okay, now any radiation which leaves this first surface won't come back to this surface 1 again. So it will come back, but it will come after reflecting from this first surface, and if it reflects back from the first surface, then we will treat it as F21 and this is F11. So since none of the radiations leaving this outer surface will come back to the same surface again, we write this F11 as 0. So we will be putting this F11 equal to 0 in this additivity rule, and it will give us 0 plus F12 is equal to 1. Now we will be using this reciprocity theorem, that is A1 into 1 is equal to A2 into F21, and we have been asked to find F21. So this will be equal to A1 upon A2. Okay, so I'll just make you understand that why F11 won't be equal to 0. Okay, now let's consider this simple vertical plate. Okay, this is my first plate, and this is my reflecting surface. Okay, so if this is a black body and it emits radiation, then I will call it as F1 and M. So M is any surface over here. So if this is my flat plate, this radiation won't ever come back over here without reflecting. Okay, so in this case I will call this as F1M is equal to 0. Similarly, if my surface is like this, then in this case also my F1M will be equal to 0. Now let's say if my surface is curved like this, and the inner side is a reflecting one. So if my radiation is coming from this curved surface, it can touch this, and in this case F1M won't be equal to 0. Okay, now let's say if I'm having two objects, that is 1 and 2. So and if a radiation F1M is emitted from here, then it will come back to this surface again only after reflecting via this surface. And if it reflects back from the surface too, then ultimately we will call this as F2m, because this radiation is coming from the second surface. So in this case also, this F, for this two body case also, F1m will be equal to 0 and F2m won't be equal to 0. And in our question, we have been given these two spheres, and for the first sphere the radiation was occurring through the outer side, and for the second sphere the radiation that is the reflecting surface is the inner side. That is why if a radiation is being emitted from the first surface, it won't come back to this first surface. It will come back to the first surface only after reflecting from the second surface, and in that case it will get changed to F21. That is why we are treating F11 is equal to 0. Now in this case you can't call this F22 will not be equal to 0. Okay, F22 won't be equal to 0. Similarly, F12, F21 won't be equal to 0. Only F11 will be equal to 0. Okay, now since it has been understood, then we can move on to the solution. So yes, now we have F11 equal to 0. That we will put it over here in this equation. So that will give us F12 equal to 1. Then we will be using the reciprocity theorem to give us this correlation. F21 is equal to A1 upon A2. And the area is the surface area of the sphere, and it will be 4 pi r square. That is, for the first sphere it will be 4 pi r1 square, and for the second sphere it is 4 pi r2 square. 4 pi will get cancelled, and we will be having r1 upon r2 whole square, and we have been given the values, so it will become 0.1 upon 0.2 whole square. Ultimately it will become 1 by 4. That is the fraction of radiation energy leaving surface 2, which reaches surface 1, F21, we call it as, it will be 1 by 4 from over here. So the final answer we can report it as 0.25, since we have been asked to report it till second decimal places. Okay, so I hope this answers your doubt in the question. If you have any doubts related to any of the questions discussed today, you can ask, or else we can conclude today's session. So this was our first question that we discussed today, in which we were given this heat exchanger, and we had to use this basic heat balance equation, that is Ui Ai into delta T is equal to U naught A naught into delta T, and that would basically give us Ui Ai is equal to U naught A naught, and based on the given information we were asked to find the overall heat transfer coefficient based on this outer area. So in the second question was the simple straightforward definition of this black body radiation intensity. Then we had this formula for this local heat transfer coefficient that you need to derive from over here. Then we had this question related to nucleate boiling. Then we had this simple question related to this resistance across the conductive resistance across the slab. Then we had this question related to boiling, in which we had to use this Nusselt's equation for film type condensation, and this question we haven't looked. This was simple straightforward experimental question, and this question was related to view factor. So if you don't have any doubts, we can conclude today's session. If possible, say again f12 equal to 1. F12 F12 won't be equal to 1 in this case. Acha, हाँ, F12 equal to 1, this will come from this correlation. So basically if we are having two surfaces, acha, okay. So if you don't have any doubts, then we can conclude today's session. Thank you everyone for joining. Okay. Let's end today's call then. Bye everyone.